Thank you. Thank you, Sebastian, for the invitation. Thank you guys for coming in this awful weather. So anyway, this is joint work with Juliana Assunção, who is an economist in Brazil, Lars Hansen from University of Chicago, and Todd Manson, who is a computational scientist, they call themselves, computational scientists at Argonne National Lab. So, you know, the Amazon forest contains about 123, all those things have big error terms, okay? 123 billion tons of captured carbon, which can be released to the atmosphere. That's the amount above and below ground. And the Brazilian Amazon is about 60% of the Amazon. And within the Brazilian Amazon, as an area of the size of Texas has already been deforested. This works better in the United States, where people think of Texas as being something very big. I think you have provinces which are bigger than the state of Texas here, I imagine.
Yeah.
But anyway,
Texas is big.
Initially it was logging, now it's mostly for cattle. And the Brazilian Amazon is today a source instead of a sink for carbon, okay? So, no, this way. So this graph is just to show the following. If you graph GDP per capita of all the World Bank gives you all the countries that they measure GDP per capita and emission per capita, you see that the Amazon is the region of the Amazon, which is not a country, but it's completely off the scale. So you see they actually are very poor, but emit a lot of carbon. Most of that is for deforestation, of course. So let me make a short summary of this talk. I'm going to talk about the optimal strategy of forest preservation over time and space in the Brazilian Amazon. I would study the problem of a social planner. So I'm not really solving any totally the social problem, because I'm thinking of somebody who's like a dictator. What choices would the social planner make? Then, of course, there's a question of implementation, which is something else that we have to think about. So I'm going to analyze a dynamic model across heterogeneous regions in the Amazon. The important thing is that when you look at the level of detail they're going to look at, the Amazon is very heterogeneous. Okay, so in thinking about the problem, you're going to have a lot of state variables because you have a lot of regions in the Amazon. Now, one interesting thing, and I won't go into this in detail, there's a lot of data on climate these days. Just to give an idea, you can figure out how much carbon is in a region in the Amazon, which is 30 meters by 30 meters, a pixel of 30 meters by 30 meters. Okay. So you have more data that you can actually use, in a sense, more detailed data. The economics, of course, restricts, because sometimes you need economic data too for this kind of work, and that makes it less detailed, but that tells you that you have a lot of data. Now, I want an answer. So a lot of it is going to depend on numerical methods. I want numbers. I want to produce numbers, and so that's what we're going to be at. Now, the basic challenge is that you have to accommodate heterogeneity of all the subregions, and in the end, you end up with a lot of solutions at boundaries. So you can't use the usual, PDE approach, because you have to deal with the boundary questions explicitly. So I'm going to produce results in three levels that I'll show you. One of them is going to consider, just for you guys to count, who have basically as many, it's a little bit more, but think of it as having as many as twice the number of sites. So if you have 1,000 sites, you have 2,000 plus state variables. If you have 80, so there, we're not going to be able to do anything with price uncertainty, so we're going to look at purely deterministic model. Then we're going to think about price uncertainty, and there we're going to think about 81 sites, and there we're going to use a technique that I just learned and in the last few months, which is called model predictive control, which I know it's familiar to some kinds of engineers. That's where I learned the literature, some nuclear engineering, but also some motive plant problems. And I'll talk a little bit about that. And then we're going to talk about models where you don't know what the value of parameters are. So there's pervasive uncertainty about the level of parameters. And then use robust control. For that, we're going to talk about only 10 sites. So we're going to aggregate the whole Amazon into 10 sites. Okay. So here's notation, just to remind us, just so you can follow what's going on. The sites are going to be denoted I equal 1 to I, and the state vector is going to have three components. It's going to be Z, which is going to denote the amount of agricultural area, the agricultural area inside I. It's going to be X, which is going to be the amount of carbon which is captured inside I. And then it's going to be PA, which is the price of agricultural goods, which is how you're going to measure the value of agriculture in these regions, okay? So I'm going to think about two controls. In fact, there's only one control, but with one control, things become, the system is nonlinear, and you can linearize at least the dynamics you can linearize at least the dynamics by adopting two controls. One control is a control, a flow vector that increases in the stock of agriculture. And then the V is a flow vector of decreasing stock of agriculture. So the stock of agriculture is going to change as U minus V. But that's just to have two positive guys, and that's going to make some things look linear. It doesn't make the problem any simpler, but it's good when you're programming, basically. It's useful when you're programming stuff. Okay, there's going to be state constraints. The maximum area of agriculture has to be the area of agriculture has been non-negative, and there's a maximum area, which empirically you get by looking at the projection, the size of the area, and then you take away things like rivers and lakes and so on, which cannot be made into agriculture and also don't capture carbon either. So that's the Z bar I is the area of site I, and you have the state constraints. The way you wrote it, every site has to be non-negative with each one of them. Okay. And then finally, you have to think about the carbon capture dynamics. And what the carbon capture dynamics is trying to pick up, these are equations that comes from the people that works in the biology of trees and so on. And there are basically three components to this dynamics. The first one is that if you deforest, you know, UI is the control that says that you are increasing agriculture. So you are deforesting. If you deforest, you immediately have a loss of carbon, which depends on the site. Okay, I'll talk a little bit about that, but that's part of heterogeneity. There are certain areas of the Amazon whose sites, usually because of condition of heat and rain, etc., they tend to be better capture of carbon. And other areas are worse captures of carbon. Those numbers are gamma I. By the way, there's no parameter in this model that we think of, okay? With one exception, tell what it is. Everything else is from data, okay? You look at the data, you can estimate those things, okay? So that's the loss in site I is going to be minus gamma I UI. There is a certain amount of mean reversion. If you think about gamma I being the capacity of capturing carbon, trees will grow. Eventually, you exhaust the amount of carbon you can capture on the side. You don't have an infinite tree anywhere, okay? So the basic idea is a stationary forest should not capture any carbon, okay? That's the way it works. And so you do that through two terms. One is like a mean reversion term, because you don't want your forest not going to get infinitely big. And the other is that the amount of carbon, maximum carbon you're going to capture in a piece of forest, which is the third term, is going to depend on the parameter alpha. I'll tell what the parameter alpha is in a moment. It's going to depend on gamma I, which is the amount of carbon that site is capable, times the total area that you kept without agriculture. Eventually, you're going to get there. The alpha is the speed at which you reach this maximum size, and the literature says that you reach 99% in 100 years. Okay, now they think about the thing. They don't think really of a negative exponential like we tend to think about to make things simple. They think of something that grows slowly, but they don't give you really a formula. But that's where you come from if you fit an exponential, right? Negative exponential. Now, there's the agricultural land dynamics. The amount of land that you are going to capture to agriculture is going to be the amount you put into agriculture minus the amount that you take out of agriculture. Of course, something is going to be very obvious is that at the optima, you're not going to do both. You do one or the other. And the logic here is kind of easy. When you cut, you immediately release carbon. Then what's going to happen if you decide to put it in an instant again, you're going to put back, without agriculture, it's going to grow. It's going to grow slowly. You're going to achieve what you cut. Discounting takes care of that. So you never want to do that. It's never optimal to do that. Okay. So those are our first, the model. We're going to think of the price as being some kind of continuous time Markov chain. That's not going to play much role in what we're going to see today, but that's there. And then there's agricultural output. Agricultural output depends on the amount of agriculture you have. It's linear on the amount of agriculture you have. It's going to depend on the price of agriculture, but it also depends on a site-specific productivity parameter. So this productivity parameter you get again from data. You know how much meat you get from these areas per hectare. You get that stuff. And you also know the price they effectively get. A lot of it is transportation costs. So you get a theta I as a sum of the two. And then you have net emissions. You know, if you have agriculture, you produce emissions. Agriculture in this region is cattle, basically. Cattle produces methane. That's basically what a kappa is. Okay? And then, of course, you also have emissions when you diminish the area, the carbon you have in the sites. And that's just to sum up. So that's a very simple form. Okay? So kappa is the emission of hectares, what you do. And then you need some adjustment costs. Okay, and this is the form of adjustment cost. Okay, you think about having a finite number of equipment. This is all estimated from data, but I won't go into this today. You guys can ask me about it. The slides talk a little bit about it, but we won't have time. So it depends on the total amount that you are changing use. Okay. Remember, those are both non-negative. And then, of course, only one of them is non-zero at any point in time, but for every site. And then you square that, and there is a coefficient in chi, which kind of measures how difficult it is to move things around. Okay. As I said, all that you get from data. For instance, the chi you get from the idea that you have land, which is still virgin land, and then you have land in which you already have cut. So the difference between the two reflects two things. Any value of wood you may have gotten when you cut it, but also the cost of actually doing that. And you can observe in data what's the difference in price between those two things, and you get a measurement of chi. Okay, so that's and here is the optimization problem. The typical optimization problem. There's a discount factor, and there's an expected value because for the problems for which there's uncertainty. And the planner is going to choose the site-specific controls, and the planner is going to get two things. It's going to get the value of agriculture. Let me see if I can play with this. Here's the value of agriculture. PAT theta I is the IAT, but also he's going to be rewarded by a value for emissions, a price for emissions. And I'll tell you in a moment what the price of emissions come from. This is the amount of emissions, and that's the captured emissions. This I flip the sign, right? So here I have the amount of carbon that you capture minus whatever emissions you do from the area Z. Of course, X dot could be negative or positive. There's no reason to be. And then there's the adjustment cost. And the price of emissions is going to reflect two things. It's going to reflect the value that the planner himself, let's think of this planner being Brazil, the dictator of Brazil. We almost had one, so we escaped one recently. But the dictator of Brazil on one hand, and then whatever transfers are given if there's a market for carbon capture. Okay, the P is going to be the sum of the two, and we're going to think about that. Okay, so okay. Sometimes we're going to think about parameter uncertainty too. Then the problem is slightly different when you think about robust control. That's not the objective of the planner anymore. In that case, we think of a vector of parameters. It's going to be related both to the thetas and to the gammas. That is the productivity of the site to capture carbon and the productivity of the site in agriculture. We're going to start with a baseline distribution, what the planner thinks is the baseline distribution. And then given a vector, the history of controls, we think of f, d, f of, as a function of d, which is the vector history control, and beta, which is the parameter value. That gives you the value if the true value of the parameter was beta. Okay? And now you follow a max-min criteria in which you penalize using an entropy penalization for a distance from the prior, okay? And then you take the minimum expected value, counting the penalties too, of across all the distributions, all the densities G's against pi. So G is just like a Radon-Nikodym measure with respect to pi. And then you maximize overall all decision rules. So that's a standard entropy formulation. C is a primitive parameter that uses, of course, what's usually called the relative entropy divergence or the Kullback-Leibler criteria, right? So that's the what you're doing. So that's when you get to robustness. But I'm going to go back now. And then once you do that, you have formulas. The nice things about this formulation is that you get semi-analytical formulas. You get this equation one tells you what's the optimal G star you're going to choose, fixing D, fixing the decision what's going to be the optimal G star, and that produces some form of exponential tilting. So you're tilting the distribution towards the G star, which has bigger values. And then you can also compute a minimized objective. And that sometimes people call that smooth ambiguity, but that's just a name. Okay, so that's where we are here. So we do a lot of calibration. I'll leave the slides here. You can figure out how we calibrated the sites. But it's all calibrated either from data, satellite data, a lot of it is satellite data, or economic data. Okay, physical data is almost all satellite data. There's a lot of stuff here. I'm not going to spend time with that. Now, for parameter uncertainty, we have to choose a certain clustering. I'll talk about that later. But now let's talk about this variation of site-specific parameters. So there are two sets of parameters. The gamma is how good you are at capturing carbon. The theta is how good you are at producing cattle, essentially. And you can see they're kind of negatively correlated. Just looking at the picture, you get a negative correlation. But it's not that high. It's about minus 0.3. Just from a regression, which basically says you really have to make a lot of choices. It's not as if there's a bunch of land which is good for agriculture and a bunch of land which is good for carbon capture. Of course, this region here, all the way to the west, is mostly good for carbon capture, but you see there's a pretty good land for agriculture there. The south is very good for agriculture, not so good for carbon capture. So those are the relations, okay? Again, that's all come from satellite data here and economic data here. Okay, so what are the computational challenges here? We're going to present two sets of results for various P, and then I'll get to robust control finally, which I don't have full results yet. They're almost there, but not yet. So we're going to talk about results based on 81 aggregated sites, or results on 1,059 sites. Those sites are constructed from the projections from satellite data. So the basic idea is that if you look at the optimal solution, the planner is going to allocate no land to agriculture except for a few sites. The optimal policy, if you have a reasonable price for carbon, then you get to a situation where you want to put zero agriculture on a lot of sites. Okay. And that, of course, means that the constraints are binding. Okay, so how do we do that? We do first a discrete time approximation is obvious. We don't solve the continuous problem because we don't have these kind of Hamilton-Jacobi-Bellman equation doesn't work in the thing. So for the case where you have deterministic prices, all we do is that we put a penalty function as you get to the boundary and solve the problem, and then you say, okay, something we're very close to the boundary, you make it zero, make it boundary. Now for a certain price, however, we had modified predictive control. What is modified predictive control? It does the following. It takes a horizon. Maybe I should just show you a picture here. This is the next one. That's from a book that does this stuff, Tangerville. And here's the way you think about this problem, is that you have, for instance, here you have every time, you have 3 possibilities for the uncertainty. So you open 3 branches every time. And what you do is the following. You sit in there at time 0, you go time 1, you have 3 nodes, at time 2, you have 9 nodes. And now you take the state variable, the value that acquires here, the state variable, the value here, and just consider it constant for the rest of the time. That's the secret. Okay. And what you do, so you have 2 horizons. You have the robust horizon, which is how many periods you're going to consider uncertainty. And then you have the prediction horizon. Now, that's because the people doing this are doing thinking in real time. We economists do nothing in real time. We have all the time in the world. But it's a very difficult problem to compute. So what we do is that we consider the robust horizon, but our prediction horizon is everything. It's like 200 years. We don't need to have a short predictive horizon, because once we have a deterministic system, you can just compute it. Okay. So here we're doing a yearly steps, and the prediction horizon is 200, but the robust horizon is 6. How do we write at 6? You try 1, 2, 3, 4, 5. When you get to between 5 and 6, the value of the problem is changing very little. So it's what I call faith in concavity, right? If we believe that this function, even though a discrete function, but behaves like a convex function, so the difference, that's concave function, the differences keep falling. If they are always smaller than the previous one, and there's no point where it goes back there. As far as I know, there are no theorems of that kind. I couldn't find any theorem where people will, those are discrete problems, they're hard to do, but I gave this talk once, and Taki Suganidis who is a mathematician in Chicago, was very puzzled by this story. He thinks that it has to be true, but I don't know how to prove it, okay? And then you just do the usual control. I'm not going to go into details for that. And then, so the way this works, and this is very important, which I haven't said yet, is that you do the robust control, okay? You choose the first period choice. Now you start again. Again, you take 2 periods ahead, and then the prediction. So you're rolling over. So only keeping the solution for 1 period, okay? So we have 6 periods of robust control and 194 periods of prediction control, extra periods for prediction control, total 200, right? So what we do is that we solve the problem at 0, considering 6 nodes. Okay. In this problem, we only have 2 branches, so you get to the 6. So you get these 2 to the 6 nodes, and then constant from then on. That only gives you the solution for the first period. Now you roll over the same way. Now you start at period 1, you do 6 periods of robust control, 193 for the rest of the predictive, and you keep doing it, okay? And that's how you solve the problem. So,
Jose, can I ask a quick question?
Sure.
Just about the terminal condition at the end of this 200-year period.
What do we do?
Yeah.
Okay, our objective is easy to figure out. It's bounded, below and above. So for 200 periods, we can put it at 0, or you can solve the Hamilton-Jacobi-Bellman equation from then on, ignoring the constraints that give you an upper bound, the other gives you a lower bound, and then you stick to it doesn't make any difference. But that really depends on the fact that our objective is bounded in every period. Okay, the Amazon is finite. You could make it all carbon, and you know what the value of that. You can make it all aggregate, you know what the value of that. Sum the two. If you could magically have both at the same time, that gives you the upper bound. Okay? And after 200 years, they're not worth much, even though it's a big number. After 200 years of this. By the way, the one number we don't calibrate ourselves is the rate of discount. And economists use 2% everywhere. We try with 3, doesn't make much difference, but that just to tell you that that one we didn't look at the data for that. Okay, so all right. The robust problem, it's a little bit different. You have to compute in a different way. First of all, we have no uncertainty, so we don't use MPC. I mean, we have uncertainty about the parameters, but no uncertainty on the prices and so on, no kind of usual uncertainty. So the way you solve the robust problem, first reverse the order. The min-max theorem helps you there to reverse the order. So now you take the min of a max, okay? We fix the G, we fix the density, how much you want to change the density from the original, you know, what's the radon-nicotine derivative it will be. And then we solve the maximization problem to obtain a D. Notice that when you do that, you can ignore the penalty because the penalty is D independent. So just figure out which D maximizes the stuff. And then we start with the D, go back, solve the minimization problem. Now we put back the relative entropy term. And here, it's very hard to compute, and partly because at equation 1, let me see if I can go back to equation 1. This is equation 1, okay? What's tough is to compute the denominator. And that's when Metropolis Hastings is great, because Metropolis Hastings, you can choose a function, instead of looking at the density, you look at something that's proportional to the density. So G, which should integrate to 1 against pi, doesn't have to, you cut the denominator down, which is constant for all betas. That one, you can do it. So it's like, works perfect for this problem. So you use Metropolis Hastings. Now let's go back. Okay, and then you it's like for an economist, they are, because I never work with those problems in economics, but many economists do use this method to compute Bayesian posterior in terms of a prior and a likelihood, okay? And then you repeat the step. Now you got the G, go back, can the D until the stuff stops moving. So that's what you do with the robustness problem. Okay, so here's what the robustness problem does. It's kind of interesting. You start with a prior. Our prior is normal, okay? And here I'm looking at different sites. Every site, you have a prior over the site, okay? We're assuming them to be independent. But when you maximize, you use the 10-dimensional vector, everything. So the beta is actually 20 dimensions. This is only on the gamma, so there's 10-dimensional beta. And then you use this system, and that's what it's going to do. It's going to tilt the G is like a radon-nicotine measure, so you're tilting the distribution. So for some sites, almost nothing happens. For other sites, you change a lot, so you become much more pessimistic about the value. That's what's happened the other sites. Now, we just figured these numbers were produced to me yesterday, but I had played with other stuff, and I'm pretty sure that happens because that really depends what you do under the prior. If you take the prior and you have a site that you reforest a lot, this problem where you penalize, but allowing people to look at the worst case of the penalization, right? Then you tend to become very pessimistic about the gamma. Whereas here, which is you put much more weight in small values. Where there you put more weight, that you don't do much. That's my conjecture. I'm not sure of that. I'll know this tomorrow when I look at all the stuff, have time to look. I got this last night, so I didn't really have time to look at it. Okay, now, so here's the problem. We have 15 minutes, right? Okay, so it's plenty. First thing I wanted to ask is that how much Brazilians value the forest? Okay, that's the first question. Now, of course, that really depends on the government we have, but we can look at the average to figure out how much Brazilians themselves value the forest. We have a problem to solve. We could say, look, We started in 1995 because Brazil was has always been a crazy country, but it was particularly crazy pre-1995. We had rates of inflation that went from 100% a month sometimes higher. So they kept changing the currencies. And I can tell you this, it's impossible to go back and realize what those prices really mean. So after the stabilization program in 95, we could actually measure stuff, okay? So that's our first date. 2008 is an interesting date. It's a date in which some countries, mostly Norway, a little bit Germany, and even less United States, but those three countries decided they would help reforest the Amazon. So there you're getting something. It's not a very big program, but we thought, let's see, before that program, how much Brazilians themselves value the forest. So what you do is that you take our problem, right? Start with the initial conditions, what prevailed in 1995, right? Take as several values of what you're trying to find out, which is the PE, the Brazilians value the stuff, and look at what happens in 2008 and match deforestation. You get a number. So that's the number that explains the quantity of deforestation you got between 95 and 2008. Okay, that number is about $5.76. Don't be fooled by the precision, okay? It's not that precise, but it tells something between $5 and $6, okay? You have to use a number, you use a number you calculate, but I'm not gonna come here say, in fact, I think we use 5.75, because when you look at the grid with the quarter dollars, but whatever, okay? So that's what you get. It's pretty low if you think about it. If you think that right now in Europe, you trade carbon at $60 a ton, this is the price, the Brazilian's value is like 5, and let's call it 6 if you want. It's pretty low, okay? So that's the first thing. Most people think that to get things done, we're gonna have to elevate that, to raise that price to something like $200-300 a ton. That's what people think. We're gonna talk about some of those numbers later, okay? So that's the, for those of you who are, since this is a finance seminar, the only finance here is the methodology in the end, but there's no finance here. But there's one fact about finance, is that the discount rate you use, okay, the higher the discount rate, the lower the price. Why? Because carbon, emissions of carbon is what a finance guy will call a low duration process. You emit today, the cost is all today. And agriculture is a long duration process. So when you raise the discount rate, agriculture becomes less valuable. To explain the same deforestation, you must make carbon less valuable. Okay, that's what this number comes out. Okay. All right, so that's our first thing. Now, I can tell you the following. What would happen with the Amazon if we kept, now can move the program forward. We can take that price of 576 and say, okay, what would a planner do if the price is 576? And the answer is a disaster, because they will increase deforestation. Nowadays, about 15% is occupied by cattle. Cattle and other forms of agriculture. Cattle is 90% of the total. But let's talk about cattle. And then they're going to increase from 15 to something like 27, 28% in 50 years. But what that means is that, you know, the scientists think that between 20 and 25%, the Amazon forest would tip, will stop being a tropical forest. And then there's a lot of discussion, either poor forest or a savanna. They haven't figured this out yet, okay? Both of which are very bad news for the rest, for the climate of the world. You know, nobody knows what happened with the El Nino when that happens. Nobody knows what happens to the Gulf Stream, which should make Europeans very nervous. Something happens to the Gulf Stream, okay? So that's a problem. So that's the business as usual, the black one. Now you ask yourself, what if I add to the number PE transfers? So you can add $10, you can add $15, or you can add $20. Those are three graphs there. You see, then you reforest substantially. You diminish the area to the, in the case of the $20 or $25 transfers, you are, I'm sorry, 15, because 576 is the original price. So that's $15 of transfer, this is $20 of transfers. So 15 and 20, you basically reforest the whole area. Okay, so that's the first thing to think about. Now, you can also calculate how well Brazil will done under those scenarios. And it turns out that the value function with respect to the PE, it has to be convex. That's just a fact, because of the support function, essentially. So that's PE. The Brazil is here. If you give them $10, you're actually here, so you're worse off. Okay. But you give them $15, it's not in scale. If you give them $15, then you are over the hump. I think, I'm not sure $10 is here or here somewhere. Could be that 10 is here, and this is 15. Okay, so this one is a bad deal for Brazil, because you're doing worse than you've done by yourself. So they'll never sign a treaty in which they promise to receive $10 for every unit captured and pay $10 for every unit they emit. We pay 10 to receive 10 for net units. Because their optimal program under that, they would emit much less, but they would be worse off. So that's the first thing to think about. So you have to have a big enough transfer, but it's not that big, it's $15 compared to the prices that cost to capture carbon nowadays. That's good. The other thing is what happens. This is the occupation of agriculture of Brazil. Okay, and again, this, if you take 576, you have this graph here. Let me try to do the magic here. I like this. This is the initial condition of occupation. This is what's going to happen if you leave at 576, just the Brazilians in 50 years. This is what happens if you transfer $10. This is what you happen if you transfer $15. And this is what you happen if you transfer $20. Now in this graph, you see the binding constraints. There's a lot of zeros in this graph. Okay. It's just from the nature of the problem. Okay, so that's good. So next, I'm going to show you, I take a price, which is the $15 transfer, the 2076, and see what happens over time. And you can see that what happens over time is pretty fast. You start here, that's today. You get to that number in 2076 by, 2022. By 2027, you already have done substantially. By 2032, which is 15 years, after 15 years, you have almost done. And in 20 years, most of the areas are no longer occupied, mostly zeros. What it says that most of reallocation occurs in 15 years and almost all in 20 years. That's very important, because the problem we have now with climate is what to do in the next 30 years. 30 years from now, we're going to have Bill Gates' magic machine. We're going to capture carbon from the air, then we can do whatever we want, okay? But for the next 30 years, it's very unlikely that that's going to be available. Now, this just tells you what's happening with Brazil. And let's pick a number here, like 2076, and a price for agriculture. Let's pick, I'll choose a line here. No, this one that I need, right? Okay, so I'm going to look at this line. That's a transfers of $15, okay? Agricultural output goes, today is about $5 billion a year, goes to 660 million, almost vanishes. That's the discount, I'm sorry. This is 660 billion is the discounted value over 50 years. Okay? But most of them, so that really so compared to the original, if Brazil stays in the business as usual, there's a big loss in terms of agriculture, but there's a gain of net transfers. The gain is in climate service in Brazil, which I evaluated at 576. That's what Brazilians value. Okay. And so you see the planar value, the final planar gain, and you can see with transfer of 10, which is this price of 1576, the value goes down. But with $15, the value goes up, and with $20, it goes up by a lot of transfers. Okay. So I'm not going to spend time on that. Now I want to think about net transfer. I'm just going to tell a little story. A friend of mine to whom I explained this result gave me the best explanation. He said, look, if you are in a hole, you're digging the hole, and then you decide, I want to go back up, for whatever reason, okay? The first thing you do is that you stop digging, and then you try to do whatever you have to do to back up, right? If you think of that, that's like the gains from trade. So Brazil be paid per ton of carbon that the forest effectively captures from now on. But one of the things you do when you have a price which is high enough is that you decide that thing I was doing in the past that was destroying the forest, I'm not going to do anymore. So to do the right computation, you should compute the following. This is how much billion tons of CO2e Brazil would capture in business as usual. It's a negative number, which means they will emit 31 billion tons over the next 30 years. That's accounting for 30 years. Okay. But with this program, they're going to capture, for instance, if you pay them $20 that you've been talking about, they're going to capture 16. So the difference is 40. Okay. So effectively, the cost per ton, instead of being 15, or instead of being 20, is going to be 676. Because, oh, this was a mistake. What did I do here? Yeah. So I'm back here, pointing the right thing. They're going to get, let's suppose, 15 per ton, we're talking about before. They're going to capture 14 billion tons. They were in path to emit 31, 32. The total is 48, okay? And so the effective cost is only $4 per ton of change, which is extremely low if you think about $4 per ton of change, okay? Now, that's what we economists usually call gains from trade, okay? Brazil is, so any price between $4.76 and $60 is a price at which both sides win. Europeans are paying $60. They could get stuff for $4.76. Any price in between is a transfer price which is reasonable. Okay, if you think about the way the Nash solution, you go halfway. Okay, between 476 and 60, 32. You could get a transfer 32 in a Nash solution. Okay, but you could get any, and 32, Brazil would be incredibly better off, and so will be the world because they're going to stick at 32. So to finish this. That's the uncertainty. You get the same picture. Okay, I'm not going to spend time on this. You get that's now with 81 sites when they solve the uncertainty. I want to make one more point here. Oh, this is wrong. Okay, just finish with a couple observations. That's the same value decomposition I showed you now with the 81 sites. The numbers are very similar. So uncertainty doesn't add a lot to this problem at this stage. But I want to make one more point looking at, no, I think I'm moving the right direction. So I want to look again at this table where you get this. So you get from this, you're getting something like 48 tons. Now, if you look at the last IPCC, it just came out this month, right? Report. What the IPCC report says is that in 2000, to have a 50% chance of warming, of not passing 1.5 degree warming since the beginning of the industrial era, okay? To have 50% chance, we can only place another 500 billion tons of CO2 in the atmosphere. That wasn't, but that was in 2000 when they did this calculation. The report came out 23, but this calculation was done from 2000. Okay? Now, we put about 40 a year. Okay? So that's 3 years. We're kind of advanced in 2023. By the end of this year, you have to take 120 out, so we're down to 380. So we're talking about numbers here of the order 10% of that number, 7% of the IPCC 510, and almost 11% of the what we have now. Those are huge numbers if you think about it. That in the next 30 years, you can do 10% of this margin. You can increase the margin by 10% if you just do that. So that's cheap carbon and it's big carbon. It's not a small amount, okay? So that's the end of my talk. I just want to make sure that that's, as I said, those at modest price for extended carbon, Brazilian Amazon who produce noticeable CO2 capture. This compare, I just gave you the compare the IPCC budget. There's also some work on natural climate solutions. When they work on natural climate solutions, the typical price they take is $100 a ton. We're talking about 4, so 476, call it 5. Okay, so it's very, so fact is that this is just Brazil. If you take the large tropical, there are 4 large tropical forests in Brazil. There's the Brazilian Amazon. Second inside is the rest of the Amazon, which is mostly in South America, but some of it also in Central America, places like Venezuela, Colombia, Peru, Ecuador, etc. And then Bolivia. And then there is the Congo, and then there is Indonesia. Roughly, you know, that more than doubles the Brazilian Amazon. Maybe 2.5 times the Brazilian Amazon. So if you look at those numbers and think that similar numbers, we don't have data for that, we haven't done it, but similar numbers should apply to all these tropical systems. Now we're talking about big numbers, right? Because we're talking 4 times what, 2.5 times what I said about Brazil. So we're talking about, you know, 1/3 of our carbon budget, something like this. Okay? Thank you, guys.